Let's see, who has the roughest end of semester right now? Most stuff going on. What do you have going on, Jake?
Oh, then someone decided they like my scooter, so they took it.
Oh, that is rough.
And then the flu is everywhere.
Yeah, lots of people getting sick after Thanksgiving. My kids got sick, got the flu. So we've been dealing with a lot of fevers in our house, but they're all better now. Okay, so we only have 3 more class periods left. We've covered everything for this upcoming midterm exam. Today in class, we're going to talk about your last project. We're going to combine the web search PageRank project that we did way long time ago with something called word embeddings. A question, Kieran.
Do we have to clone the repo for this assignment?
This question is, do you have to clone the repo for this assignment? The answer is that you're going to be building off of your previous PageRank project. So you should all have your own repository for that. And my recommendation, I recommend just building off your previous solution, but I have also included in here my solution to the previous problem if you would like to use that. And so again, combining PageRank stuff we did way at the beginning of class with the stuff from these last 2 midterms, seeing how it all fits together. That's the goal of this programming project. Again, I think the in terms of like coding wise, it should be a relatively easy project in the sense that there's not a lot of lines of code that you have to write. I think the total amount of lines of code is going to be like between 10 and 20 maybe. Yeah, if the first PageRank problem was particularly hard for you, then expect this one to be similarly hard. Due dates, so the not this coming Sunday, but the following Sunday after today, we should have covered everything that you need for this project. So you're welcome to get started. I'll just ask you to not collaborate on the project during the midterm 3 time period this coming weekend. A bunch of references here we'll take a look at in a little bit, but we'll start off just talking about like what the project here actually is. So the first task, finding similar words. So as a reminder, if you're running your PageRank.py program, you can specify like particular search queries that you want to look for, like looking for this word weapons right here was one of the examples that we did. And it's looking in the URL for times when the word weapons appears in the URL, and it's only returning things that match that filter. And then the way that PageRank came into this is we ranked all of these different pages and gave them their PageRank score, and we only displayed the things with the top PageRank score. So this was the output of something like weapons. Here, the output of something like drones, giving you a totally different set of results down here. Targets, another totally different set of results down here. And again, in this case, I chose those particular 3 examples because the results don't even overlap at all, but their like semantics is very similar to each other, that you might expect that if you're do a search for weapons, that you might get results about drones or about targets as the outputs. And so the idea of this first task here is that we're going to want to find synonyms, whatever like the person types in as their search term. We're going to find synonyms for that first term, for that search term, and search for that as well. There's this GenSim library that you'll use to do this. And the code for doing this, very simple. It looks something like this. So you just import the GenSim. This gets us a model. We'll talk about in detail what this is actually doing here in a little bit. But these are the only 3 lines of code that you'll need in order to do this. And then this most similar function here, we have weapons, gives us things that are somehow similar to weapons. This thing on the right here is a score. Again, we'll talk about what that means in a minute, but for this first task right here, the only thing that you really need is this first leftmost column over here. And then if somebody types in weapons, you'll do a search, not just for weapons, but for also the top results in this. Any questions about that at a high level? Okay. Yeah, so the code again for this should be relatively straightforward. What we're going to spend most of today talking about, though, is how does something like this most similar function get implemented in practice? That it seems like it would be very hard for us to just write out some code that finds synonyms of words. But this whole idea of like the last 2 midterms that we've been talking about is how can we use machine learning to somehow learn these hard functions for us so that we don't have to do this by ourselves. We don't have to do it manually. And so we'll, this function right here implemented with machine learning. The specific example is this word2vector, these word vector systems. And so we'll talk about that today. One last note, though, this task 2 down here, another task that you'll have to complete, besides just doing that filtering on the synonyms, it also makes sense to rank pages with a higher similarity, higher in your results. So not just doing the ranking by the page rank, but also doing the ranking by the actual contents of the words. And this task 2 is goes through, talks about how to do that. Complete those 2. Yeah, task 2, there's pseudocode that you'll have to write up here. Again, should be super short. So my hope is that this won't be like a super stressful project for you at the end of the semester here. Do those 2 things. You modify your GitHub repo to include your modified PageRank file, and then the README from your previous project had a bunch of sample queries that you were supposed to run. You'll just rerun those sample queries with your newly modified code and upload your GitHub repo to Sakai to submit. So yeah, at this point, we haven't talked about like what this most similar function is doing internally, but outside of that, are there any questions about like what the project is asking, what you'll need to do for the project? Okay.
Well, if you try and do like the Jensen, import Jensen.downloader, I said it's missing something called the NumPy testing tester.
So in order to use Jensen's just a library, pip install Jensen, and then it should install everything that you need. If it didn't install everything that you need, then something's broken with Python, and I can take a look at that for you separately, but just pip install Jensen should get it to work.
You suggest doing this on the own machine?
Oh yeah, of course, you can do this on your own machine or on the Lambda server. Some of these, so this most similar step right here is a relatively slow thing to do. So it'll go faster on the Lambda server, but by relatively slow, I mean like, I don't know, on the order of 5 seconds maybe. So up to you on, I would do it on the Lambda server because I don't know, seems it's easier for me to work on the Lambda server than it is on my own laptop. But if you disagree with that, then if it's easier for you on your own laptop, do it on your own laptop, and that's fine. Some of these models that you'll be loading can be multiple gigabytes. I think some of the bigger ones are on the order of like 10 gigabytes or so. So you might eat up a lot of disk space on your laptop if you do it on your laptop, and you won't have to deal with that on the Lambda server. Good questions. Any other questions about what the project, high-level things about the project, what to expect, what to submit? Okay, then we're gonna focus rest of class today on this most similar function, what it's doing internally. And it is using this word2vec system. The main reference that you'll want to use, and that we'll be going over today, is this link right here. But there's a handful of other things as well that may or may not be interesting. And if we have time, we'll take a look at some of these other ones as well. But this one right here is the main reference. If you click on that link, you'll come to this web page over here, The Amazing Power of Word Vectors. I just want to highlight historical note for us first that so these 5 papers down here are the ones that first introduced this idea of word vectors. And so this one up here in particular is the very first one. And the timing of this, 2013, happened just months after that AlexNet deep learning system for ImageNet came out that we talked about during the transfer learning topic. So this paper published January of 2013, AlexNet published end of September 2012. And both of these two things, like at the same time, before this, nobody had heard of deep learning at all. But then after this, deep learning became super popular. So it's AlexNet on ImageNet made deep learning popular, but also this idea of word vectors made deep learning popular. And so this was the time period that happened at. If you look at the citations of this this original paper, it's one of the, I think it's like number 2 or number 3 most cited papers in history, 31,000 citations. The author's up here, Mikolov. He's a Czech guy, the main author. That's what he looks like. He bounced around. He did this work at Google, but then immediately left for Facebook and Microsoft, just spending a couple months at each place. And basically doing the same sort of work everywhere. The other super famous author here, the last author, Jeff Dean, is the head research scientist at Google. So he's another super famous person. His salary is not publicly disclosed, but credible estimates are like greater than 40 million a year. Yeah, like an NFL superstar. Okay, so now we're back to this this amazing power of word vectors webpage. I've just scrolled down a little bit, and we're going to go through a bunch of the images in this webpage that sort of highlight how the system works and why it's cool. So this right here, this first image is just an image of the one-hot encoding that we've talked about before. So if you had these 5 words in your data set, woman, child, man, queen, and king, then each one would correspond to a different dimension in a feature vector. And here, if we're trying to represent the word queen, we would put a 1 in that column and then a 0 in every other column. If we're trying to represent the word man, we'd put a 1 in this middle column and a 0 in every other column. The upside to this is that it's super easy to do. The downside of this is that the vector here has no semantic meaning to it. And all these words are totally, if you were to calculate the Euclidean distance from one word to the next, they would all be exactly equidistant from each other. But semantically, these words probably shouldn't be represented as things that are totally equally distant from each other. That the words king and queen seem a lot more related to each other than, say, the word king and child. I don't know, king and children are both people, but not only are king and queen both people, they're both royal people, and they're both adults. And so they have a lot more things in common. And so we'd like to represent those commonalities between the words somehow. This next picture right here captures one way of doing that. Now, instead of representing each word as the one-hot encoding, we have what's called a distributed representation of the words. And in this distributed representation, we have some columns that, so each of these word vectors here, the particular elements in the word vector have some sort of semantic meaning to them. So we might have like a royalty portion. King, queen, princess all have high values for royalty, but woman has a low value for royalty. And then a masculinity portion, king has a high value for that. The other three have low values. Femininity, sort of the opposite, that the king has the low value, queen has the high value, and so on. And now, if we're able to do this, if we're able to construct vectors this way, then our vectors do have good semantic meaning to each other. That king and queen, we can tell that they're closely related to each other because they have this royalty thing going on in common right here. That child vector is not listed, but the child would have nothing in common with king over here. And so it would be very distant from king. This is the first key insight about word vectors that the one-hot encoding is sort of like the most dumb, naive thing that we can do. And this, if we could make something like this, that would be better for us probably. And so the question is, how can we make something like this? How can we get these word vectors for the different words? Linguists had been, before 2013, had been trying to do this for a long time, and they've been doing it by just like hand coding things, manually making these features whatever they wanted to. But if you look at Wikipedia, Wikipedia has over 1 million different words inside of it. And so manually going through and annotating all that would be way, way too much. So we really need a machine learning solution to this. It's a good spot to stop. Questions? Any questions about like this distributional representation right here? What it means? Yeah.
So we like basically instead of representing it as like a one-dimensional 1 to 1 or 0 scale, we like expanded it to 2-dimensional, where each entry here is like a vector itself.
So each word is still a one-dimensional thing. So here's the one-dimensional word for queen. They only have one of the data points shown here, the queen data point. Here, the queen data point is still this one vector right here. So the dimensionality of each data point is still the same. It's still just a vector.
So what would that previous data point look like?
Yeah, so I've just switched over to a blank page over here that if we had in the one hot encoding, something like king, queen, child, each one of these having its vector, something like this. These are all rectangles, I promise. And the length, the size of these rectangles would be V, where V is the size of your vocabulary. How many words that you have, and the total number of vectors that you have also V. So the total number, if you were to stack everything into a matrix, the matrix representing all this would be a V by V matrix, whereas in the distributional representation, it's the one hot on the left, distributional on the right. King, queen, child. Now they're not like one hot, they'll be like 0, 0.5, 0.5. Just making up numbers here. They could be zeros and ones, they don't have to be. And they're not required to add up to 1. I just happen to make them do that. This dimension this way is often called D, typically in the range of like 25 to 300. The V over here in the range of like 10 to the 6-ish, depending on exactly what language you're working on and things like that. But you still have V over here as the number of vocabulary words. And so now the matrix is a D cross V matrix.
So would that actually reduce the dimension then?
Yeah, so the question is, does that reduce the dimensions? And what we'll talk about on Monday, we probably won't talk about it, get to it today, is that if you were using this as your input features instead of this as your input features to a learning problem, then you would have a much, much smaller VC dimension going on over here, because this D over here, even if you're like the maximum end of the range, 300, that's way smaller than 10 to the 6. So today we're not going to get to the sort of the statistical applications of this, just focusing on, I guess, a little bit more intuition about what's going on. But eventually this will be very important statistically. Statistically. Good question. And again, just very important that you have a good conceptual difference between these two representations of the words at this point, because the whole point of word2vec is how we learn this sort of representation over here and what we can do with it. Any other questions at this point? Okay. Then before talking about how to learn that representation, let's talk a little bit more about what we can do with it. And so here, this is sort of a cartoon drawing of what these word vectors might look like in just 2 dimensions. So we have king, man, queen, and woman arranged like this. And if we can make an observation here that like the difference between the word king and the word man is extremely similar to the difference between the word queen and the word woman. And I'll zoom out right here so we can see the next plot here at the same time. But this red line right here, this red line is the negative man vector. You take this man vector, put it in the negative direction, and you add that to the king vector. So this red dashed line right here is the same as this sort of red line right here, just flipped in the opposite direction, and we've added that to the king vector. And now if we add this woman vector right here, the same green vector right here, add it, that'll take us, it's not going to be exactly to the queen vector, but it'll take us really, really close to the queen vector. And equationally, what people like to say is that, and so yeah, that's equationally, not occasionally. Equationally, we would have king minus man plus woman is basically, it's not going to be exactly equal to, but it's basically going to be equal to the word queen. And I don't know, if you think about it, like you're probably more used to adding numbers than you are to adding words. But if you think about like that, then that seems like it probably makes sense that if you have this abstract idea of king, take away the maleness of that king and somehow add femaleness to it, then you're going to get queen out as a result. I'm gonna take us over to the terminal here, and we're gonna do some work with GenSim to illustrate that for a second. This is unfortunately a little bit weirdly formatted for some reason. But up here, what I've done this import gensim .downloader, and then I have 3 models loaded. This Twitter 25 model. This is the model that is referenced over here in the instructions, this Twitter 25 model. And so the first thing I'll do is just run this most similar weapons function on that model. So this is Twitter 25, right? This is the same model. These models are just the word vectors themselves. And if I do Twitter 25 dot most similar, type in the word weapons right here. This is the results that we get back. What I want us to do though is to do this particular, oops, where do we go? To do this equation, see how to do an equation like this inside of GenSim and do these computations. So coming back over here, inside of this most similar function, what it does is when you pass in one individual word like this, it finds that, looks up that word's representation, and then finds the nearest neighbors of that word in this space over here. So most similar of weapons gives us that result. But if we did, so positive, we can make it add two words together. So let's go ahead and that's a better thing to start with. Do most similar of king, prince is close to that, queen is close to that. We can make it actually do the math for us on our equation now. Positive equals king and woman, and negative equals man. So this will be king in the positive minus man plus woman, like that. And we do enter. Here, this Twitter 25 model, you can see the results not super great right here, that this is not giving us the queen like we hoped for. The reason for that is that this model happens to not be a good model. It happens to not have good word vectors represented inside of it. Again, when we talk about the training of this, we'll get into why that is the case. But I have two other models loaded here besides the Twitter 25 model, this Twitter 200 and this Wikipedia model. If we look at the Wikipedia model, wiki 200 dot most similar of king. So we get similar results here of most similar for king, prince, queen, kingdom, so on. But now if we do the actual, like the math part, positive equals king, comma, woman, and negative equals man, then we're getting this queen out as the most similar here. So most similar does this math for us. It substitutes in each of these vectors when it does this equation. So the king, whatever that vector is, gets substituted. Whatever the man vector is, gets substituted. Whatever the woman vector is, gets substituted. Subtracts off that vector, adds in woman, finds the nearest neighbor, and for a good word embedding space, we get this queen value out. Yeah, question is, what exactly is the number over here? This is the distance between the, let's see, first do it just with the word king like this. Saying positive equals king is the exact same thing as just putting in the word king by itself. This distance right here, this number right here is the distance between the word prince and the word king. So if you were to get their word vectors, so get their actual vectors, compute the Euclidean distance between those two vectors, that's what those numbers are.
It seems like the
Sorry, instead of the distance, it's the similarity.
okay.
So basically 1 over so it's just sorted in reverse order. Yeah, it wants the thing with the highest number to be the most similar. Yes, question.
I think that's one of the words we use is like the times and years paper, if we were to like times and years of anything, that just means a vector that looks, is mathematically looks and looks like a vector.
Yeah, that for so it computes these similarity scores, so like 1 over the distance between each of the words and the king over here, sorts it by those numbers, and then pick the top over here. That's the thing that's most similar. So that's the thing that we would say that we'd say that it's equal to king over here. Princess is also pretty similar to king minus woman plus man, or sorry, king minus man plus woman. It's also similar to princess, but queen is more similar to that. So queen is the thing that we would say is sort of like the answer to that equation. For the purposes of your project, you're not going to have to do these. We call these analogies. You're not going to have to do these. You'll just have to do the most similar function with a single one of these words at a time to find what the most similar words are to that particular word. But people often, one of the coolest things about word vectors is that you can do these analogies, and it was very unexpected at the time that they'd be able to do something like this. Yeah, so again, each one of these words has its own position in the space, and when you do that sort of mathematics, that addition and subtraction, you get approximately to this this other word over here. It's a good spot to stop. Are there any questions at this point? Okay. The next figure is getting into the more important parts about how is this actually trained. So we want to go from this one hot embedding into this distributed representation. How do we do that? And this is where we start intersecting with the machine learning stuff that we've been talking about. The first thing that we're going to do is we're going to set up a classification problem. Maybe the most obvious thing that we might try to do is label points as being similar to each other, as having synonyms, like queen is very similar to the word king, coming up with labels like that. That turns out not to work very well in practice. And what does work well in practice is, one of the reasons that doesn't work well in practice is that you can't get enough data. But here we're going to create a classification problem where we have essentially unlimited data. The idea is that we're given unsupervised data, usually off the internet, unsupervised text data. And so by unsupervised, again, I mean there's no XY pairs, just the X values. And we have to create the supervised pairs. We have to somehow create these Y values from this unsupervised data. Create the Y values to predict from just the X's. The way we do that is if we have a bunch of input text, say, we'll just use the example they have over here. So this is the first sentence of the word2vec paper that they have listed right here. So I'll write that down. Word2vec is an efficient method for learning high quality distributed vectors. For learning high quality, and then I have the room for the word distributed, and that's it, and that's okay, distributed. And so this is our, all we have is input text that looks something like this. The text can be from any domain, but this is what we have. And we select one of these words, we'll select method here, as the focus word. Eventually, we'll go through selecting each word in turn as the focus word, but each individual data point will be generated from one word being the focus word. Based on that one word, we'll look at some set of words around that word. So here I'll use the 3 to the left and 3 to the right. And these words over here are called context words. And in this case, the size of the context being 3 because we have 3 words to the left and 3 words to the right. Say, C is the size of the context. And now there's 2 types of prediction problems that we can create off of this. Two prediction problems. One is that given the context words, predict the focus, and the other is given the focus word, predict the context words. Both of these are classification problems that the number of classes what we have. The number of classes that we have is equal to the size of our vocabulary. That here, when we're predicting the focus word right here, there's V different possible choices here. So our output classes, the number of classes that we have would be V right here. All the theory that we've talked about in terms of the VC dimension is only related for binary classification, but adding more classes is going to make us require more data. So V classes right here. Here, for predicting the context, then it's not just one word that we're trying to predict. We're trying to predict, in this case, 6 different words, whatever the context size is over here. It would be 2 times C times V is the number of classes. In either case, it's a lot of classes that we're trying to predict. And then our input dimensions over here. So in this top problem, given the context words, predict the focus words. Their context words, our dimensions is going to be that we have C context times V. I guess it's, again, the 2C context, the C 3 on each side. And then the focus words over here, just V as our input dimensions. This first model up here is often called the continuous bag of words problem. CBOW of that you're given the context words predict the focus. And then that reverse, that sort of dual problem is called the skip-gram model. The CBOW stands for continuous bag of words. Nobody ever writes it out or pronounces it. It's just CBOW, CBOW. Both of these two things set up a learning problem for us. We haven't talked about like a particular algorithm or a hypothesis class or anything like that, but just like what the X values are here. This is the X values. Again, the given is our X's, and then what we're predicting is the Y values. Are there any questions about how this learning problem is set up, what the X's or the Y's are over here? Okay, then the way this is actually, now that we have a data set, use something like this to generate our data set. The way that we use that data set is you create neural networks. Again, that blog post has this visualization of a neural network and this one over here, one for the skip-gram model where we have a lot of inputs, a little bit of output, one for the, sorry, this is the CBOW, a lot of inputs, a little bit of output, then one for the skip-gram, a little bit of inputs, a lot of output. And the important thing here is that we have these two weight matrices, these W1s and W2. And the W1 and W2 are this V by N or N by V matrices. This N right here is what I was calling D before, what we've always called D in our class. It's the dimension of this hidden layer right here. And it just so happens, nobody has a really great explanation about why, but it just so happens that the W1, W2, again, their shapes are V by D. That blog post said N, but we'll use D for the consistency of everything else. Just so happens that these tend to make these tend to be great word vector representations. Representations, right here, representations. So it's a V by D matrix. And if we scroll up again to right here, this is a V by D matrix where each one of these rows is sort of that semantic component. And each one of these columns is one of the like actual particular words that you're looking at. Let's think a little bit about why these vectors right here might have some good intuition behind them. I don't know why this is a good way to potentially set up the problem. If we come back to this example right here, thinking about this word method, and let's think about like what are some other maybe synonyms or other similar words right here that I could plug in and it would still make sense for the word method. Well, one might be the word technique. So if I just crossed out method and put the word technique right here, then the sentence still makes total sense, still means the same thing. And we might hope that the word technique is going to appear with like elsewhere in our corpus that we're learning from. It'll also appear like next to words like efficient, for example. Talking about efficient methods also talks about like efficient techniques. But if we were to just randomly pick another word, like the word blue, nobody talks about efficient blue. So blue would never be in the context or very rarely be in the context of words like technique and method. This idea of that a word is somehow defined, or can the meaning of the word can be inferred from the context of the word, is something that linguists have known about for a long time. There's this very famous linguist, John Rupert Firth, and he had this phrase that you shall know a word by the company it keeps. And this was so he said that in 1957. That's the explicit motivation for these word embeddings and why Mikolov thought that this would be a good, potentially good thing to do. That this context over here is the company it keeps for this word. And so if we're predicting the context from the word, then that's going to be a good model for what the meaning of that word is. That's super high level intuition-y. We have basically no, say, theorems or theory about why this works. It just seems to work well in practice. And it's very much like doing research about why this works is a hugely important thing. Lots of people working on it. Any questions about that intuition? Okay, so how does this connect to the project, and how is this going to connect to what you're going to need to know on the final? Well, we'll need to be able to think about the statistical efficiency of our word2vec problem. And so I'm going to draw this the same graph I've drawn many times. If there's one thing that you take away from the course, it should be this graph right here. That on the x-axis we're talking about model complexity. Model complexity, and then on the y-axis we have things like the training error. Usually looks a little bit more smooth than that. The generalization error. And our true error. And somehow, when we're learning these word representations, or when we're using the learn representations in other tasks, we need to be thinking about the model complexity of our problem and doing the word vectors appropriately based on that. Again, we talked about many different measures of model complexity so far. So we've talked about the VC dimension, the DVC. This generally applicable for binary problems. We talked about the M for says binary classification. The M for our finite hypothesis sets. And then the different types of regularization parameters, whether it's lambda or C for regularization. And we have to control these three things somehow in order to optimize our E out based on the whether we're currently overfitting or underfitting. Which wouldn't, the right side over here, is this overfitting or underfitting? Yeah, overfitting. And on the left side, underfitting. So with our our word2vec problem doesn't neatly fit into any one of these categories. We have a non-binary classification problem, and in fact, it's very, very multi-class. Our hypothesis class is not finite, but it's infinite. It's this, we're learning matrices, and there's no regularization going on. People have experimented with regularization for this, but it turns out not to improve things for various reasons. But we did say one other, we had a sort of offhanded comment of for multi-class problems. We didn't do this formally, but we said that the generalization error is basically O of what your DVC would be if it were binary times the number of classes. So that times the number of classes log n over n. If we scroll up to the, I'm going to scroll up to our two skip gram versus continuous bag of words over here. The VC dimension is basically the input dimension over here in this problem, this 2CV and V. These neural networks that we're learning, they turn out to be linear neural networks. So the important thing is the input dimension. There's no like ReLU functions or things like that. And then this V and 2CV over here, multiply that all together, and whichever one of these models you use, you get the same sort of results in this generalization error down here. So CVal versus skipgram, they have the same model complexity. So that'll imply the same generalization error. And we don't have a good like theory or anything about why one might work better in practice than another, other than you just try both of them and see which one has the lower E sub n when training. The other more important thing, and again, this is not a formal statement in any way, but the number of, or the size rather, of the hidden layers we can think of that somehow as a measure of model complexity. Measure of model complexity. And if this hidden layer size, what did we call it? Yeah, so the D right here. If that D is increasing, that's a more complicated model. And so we're gonna have some sort of like E out that looks like this, where the optimal, this hidden layer size is our measure of model complexity. And if we have smaller hidden layer, then our EN will be really large and getting bad results that way. A very large hidden layer, then our generalization error will be large, getting results that way, bad that way. And so there's this sweet spot down here that you have to somehow find. These two concepts about the intuition behind model complexity for the word2vec system super important. So are there any questions about what makes the word2vec more or less complicated, Alex?
How do we talk about the errors of such problems when there's technically no correct answer?
Yeah, so fantastic question. The question is here, I'm using E out, EN, generalization error, all of these error terms. And in some sense, I haven't fully defined what these things are because we've been talking about these only in terms of binary classification in the textbook. But what does it mean for word vectors to talk about, say, the E out? The most simple, most literal thing to do is that you consider E out, E in, your actual like classification error on the multi-class classification problem of CBOW or skipgram, whatever that is. And the definitions all carry forward exactly the same. So that's sort of like the most literal way to interpret those variables as just if your context is an efficient for learning high, you get an error of 0. If you predict the word method, you get an error of 1 if you predict anything else, including like the word technique or the word blue or anything like that. There are more sophisticated error measures. The most common one that the most common alternative one that people care about is doing analogies like this. There are a handful of famous analogy data sets that do things like king minus man plus woman. And if your word vectors give you the result queen as the output, then you're doing well. If they give you something else as the output, then you get a high error from that. And again, this would be interpreted as a classification problem where this is your output right here. You're just not training the model directly to solve this. You're training it on something else and evaluating it on this classification problem. That's another, though, sort of open area of research about word vectors is like, what are better measurements of E out, E in, these sorts of things. And but basically, no matter what you're measuring, it's always going to have somehow this kind of curve that as your hidden layer size gets bigger, it'll start getting better performance, and then at some point it'll stop getting better performance. And there's been a lot of experimental work that just verifies this happens in lots of situations. That answer your question? Good question. No?
Is it ever in finding context words, do you ever like skip over like
Yeah, so here, when I talked about, where did it go? The continuous bag of words in skipgram, finding these words over here. There are more subtle practical things that you can do, like the word is and and for. These are going to be around like every word in the English language. They're just because they basically have no semantic meaning. They are just sort of grammatical words. And so sometimes people do pre-processing of removing these semantic words. But that's, yeah. So people do that. Hesitating because I'm thinking about doing a more complicated answer, but I won't if that answers your question. Okay. All really good questions. Any other questions at this point?
We haven't quite gone over the ways to like so that the dimensions that you're making.
Yeah, so the question is then how do we select the D dimensions that we're creating? And the answer is that whatever your output measure is going to be, you're going to have some sort of curve that looks like this. Let's see. I'm going to pause your question and we'll come back to it. The first thing that I want to do is I want to go back to GenSim over here. And we have two models that have been trained on the same data, the Twitter Wiki 25 and Twitter Wiki 200. This number over here is a representation of how many dimensions the trained word vectors have. And if we come over to this link right here, it's one of the references. These are all the models that are just available by default in GenSim. There's a lot to pick from here, but we're looking at just this one compared to this one right here. The only difference between them being just the size of the dimensions. In this case, if we look at the data set trained on, we can see, so 2 billion tweets, 27 billion tokens. A token is a word. So this means we always have one data point per word. So we have 27 billion different data points here. And that's a lot of data. 27 billion data points, that's a lot of data. So even 200 dimensions is probably smaller than the optimal for this. We could probably increase this up to say like 2,000 or so. It'd still be getting better results because the data set is so large here. But if we kept going beyond that, eventually we'd get some degradation. So back over to GenSim, if I do the Twitter 25 dot, say most similar of king, the very first words are like pretty good, like prince, queen, but then getting into weird things like AKA and lady, apostrophe S, stone. None of those things seem to really be related to the word king. But if I use the higher dimension model, then we get more, I guess AKA is still here. Burger seems like a weird thing, but you get your Burger King in there. So yeah, the literal answer to the question of like, how do you decide the number of dimensions to use is you basically just try the different things, see which ones works best for your application. How do you can sort of narrow down that search though, because there it is. It'll follow some sort of curve like this. And for English language stuff, you basically always want to use more dimensions because you're going to have super large data sets like 27 billion. And so more dimensions is going to be better. If you're using a weirder language that has less training data, so people do this for example, like ancient or extinct languages like ancient Latin. There's not a whole lot of ancient Latin that's been written. Your training data is max going to be like in the hundreds of thousands of words. Then very small dimensions end up getting better results. For the purposes of your project, I'm requiring that you not use this Twitter 25 dataset. So the one that I use, or this Twitter 25 model. You're not allowed to use this model, the one that I have as examples in the code, but you're allowed to use any other one that you want. I recommend just like experimenting around with different ones to see which ones give you better results, but you're not going to be graded on the quality of your results. Again, because it's just such a hard thing to answer like quantitatively, whether results are better or worse. Good question. Any other questions at this point? And that's okay. So another cool sort of applications of word vectors. A lot of humanities sort of people have been getting really into word vectors recently. And one of the reasons for that is because the vectors that you get as output are going to be very different depending on what input data you train it on. And so if we train our data on text from the 1900s, then we can see, and then also train a different model on the 1950s and a different model from the 1990s. We can see how the meaning of a word has evolved over time by seeing what words is it similar to. These plots right here are PCA plots, taking the top 2 dimensions of word vectors trained on those different time periods, and then plotting some of the similar words. And so you can see that in like the early 1900s, the word gay, for example, meant like daft, flaunting, sweet, cheerful. Then in the 1950s, getting a more positive connotation, coming with these pleasant, cheerful, witty, frolicsome, bright. And then now the more modern definition having the sexual connotations of lesbian, homosexual, things like that. But we can actually use things like this to measure when exactly did this change happen in time and see historically when that happened. The word, so this is a word that I think most people are probably familiar with having it changed. The word broadcast, most people are probably not familiar with that changed, that was used to be a farming term. You would broadcast your seeds into your fields, and then it became like broadcasting newspapers, you seeding information out into the world, and now like radio, television broadcasts recently. Another word, awful, used to be like 1850s, associated with religious things, God somehow, solemn, majestic, awe. Then in the early 1900s became a bad word, appalling, terrible, horrible, and now switched meanings to a positive word, wonderful, weird, awfully. And so we can see exactly when those changes happen using these word2vec projections. Another thing that people are particularly interested in with word vectors is, so they're encoding information about text documents. And here we go. Encoding information about these things. And they happen to encode a lot of racial and sexual biases that certain words maybe carry with them. And so if I come down here and we'll use the trained on Wikipedia for this, most similar. And I do the word, let's just look, what's the most, so positive. What's the most similar word to doctor? So we get a lot of like things that you might expect, things like physician, where's my cursor? Physician, doctors, surgeon, and so on. But what if we do the, so yeah, previously we did king plus woman negative equals man minus man gives us queen. We can take a positive word like king and find the associated, take a masculine word like king and find the associated feminine word like queen. But what if we do this with words that probably shouldn't have gender encodings inside of them? So if we take the word doctor, like a king is fundamentally a male thing, and a queen is fundamentally the female version of a king. But a doctor is supposed to be like a gender neutral thing. But if we do that, then we don't get the word doctor back out. That if we find the female version of doctor in our data sets, then we get the word nurse out instead of the word doctor. And for some applications, that might be what you want. That in popular discourse, the word nurse certainly has more feminine connotations, but in other applications, that's probably not what you want. So in your project that you're working on, in your search engine, if you're using this Wiki 200 model as what you're training on, and you do a search for doctor, you're going to tend to get more masculine encoded things and not female encoded things. Most search engines like Google, Bing have decided that's not what they want to have happen when people search for gender neutral terms. And so there's a lot of research on how can we generate data sets or modify the training procedure so that something like this would give you the word doctor back out and not the word nurse. Any questions about any of those sorts of humanities-ish applications of word2vec? Okay, then on Monday, we'll continue. I'll have some specific problems, learning ish sort of problems for us to talk about on Monday related to word2vec. That will be not there. You're not going to have to know anything about word2vec for your midterm, but you will have to know about it for the final. And so we'll talk about those for the final. We'll talk about the final in general over next week. And we'll have a review session tomorrow for the midterm if anybody would like to come. But that is it for today. That's a good stopping point. You're welcome.
So